This video, I want to talk about electromagnetic waves, where they come from, and how they differ from what we've been talking about earlier. There's a couple of subtle things. Most of this is going to be conceptual. This is going to be conceptual, and then we'll start digging into the math after we have an idea of the concept. So the biggest thing to start with is that accelerating charges are required to create electromagnetic waves. And sometimes you're going to hear me call those just EM waves. All right. So the idea is we need a charge to accelerate. Now, here's one way you could do that. You could take a function generator or an AC source, and you could connect it to two metal rods. And when you do, basically, I don't know if you see it, you're basically the two metal rods, that's like a capacitor, right? So you've made some kind of weird capacitor like this, where the two metal plates happen to be aligned like this. And what you're going to do is you're going to apply some varying potential to them. And as a result, the electrons in the wire, right? For example, when this plate is positive and this one is negative, maybe we get some motion down this way. And then it's going to flip a few seconds later. So then maybe they'll be going up. And then it's going to flip a few seconds later and be going down again. And so in order to reverse direction, there's got to be some acceleration. So this is a classic way to get accelerating charges. You apply an AC source to some charges in some pieces of metal, and as a result, they wiggle back and forth. Right? So another way you could think about this is perhaps you could think of them as wiggling charges. All right? To be clear, if you just take an electron and move it with constant speed, right? If you had constant velocity, you would get no EM waves. That's the difference here, right? So anytime, now you could have a constant acceleration in one direction and actually get Cherenkov radiation, where there's an electron is going from high speed to low speed, it will give off radiation as well. So there's different types of this, but I want to start with this type of wiggling charge. So to that end, let me actually go to a simulation here. Make sure I've got it up before I screen share. Looks like it's good. All right, so this is supposed to be an example of that. The idea is if I wiggle this electron, we see a spike in this field, and that's going to transmit over to the other electron, which maybe you saw it wiggle just a tiny bit. If I do this maybe more dramatically. Now watch the other electron. You see it wiggle a little bit. All right, great. So we see that this is transmitted. Now, an interesting part about this, oops, that I find very interesting. You could imagine, let's actually look at the electric field near the electron. And this is the electric field that you would expect from Coulomb's law and all that, right? We'd say that E for a charge is K Q in the R hat over R squared. And that's a vector field, right? Now notice this one is pointing into the charge. It's pointing negative R hat because Q, if we're talking about electron, is equal to negative E. So in this case, I want to point out, notice the electric field pretty much drops to zero anywhere near this. And in fact, if I wiggle this thing around, right, that electric field is so tiny, why it seems impossible that the other electron could ever be wiggling. But yet there you see on the other side of the page, after some time, the electron starts wiggling, right? And so the question was, why does this tiny electric field produce motion of that? And it turns out it doesn't. There's a different type of field called the radiated field. Now remember, where do we get this radiation from? The idea here is, we know that, well, let me stop the share for a second, right? This is what's kind of crazy. We know that a changing magnetic flux creates an electric field, right? We also know that a changing electric flux creates a B field. And this is what's different about electromagnetic, and we don't need this anymore, all right? So we're gonna get rid of that, sorry about that. The idea here is if you're wiggling these charges up and down, you're constantly changing the current. So you're constantly changing the magnetic field and thus the magnetic flux around this space. Similarly, you're constantly changing the electric field, you're constantly changing the electric flux. And so what's happening here is throughout space, even where there's no electrons present, we have a changing electric field that's creating a B field at these spots, and a changing electric field that creates a B field at this point in space. Similarly, at this point, there's also a changing magnetic field that creates an electric field, and those can interact and they keep causing this beam to propagate. So let me show you this simulation here. This is the same, oh, whoops, I gotta share it. In this case, and let me see if I can do this. The idea here is we're showing the electric field created there and the magnetic field is perpendicular to it. If I go to a straight on side view, maybe this is a little bit easier. The idea is we're seeing the electric field at many different frequencies here created. Well, the magnetic field is kind of in this perpendicular direction as indicated by those other lines. And we see it's propagating outwards throughout space. And it is these changing electric and magnetic fields associated with the wiggling charge that allows this to propagate. So if I could go back, whoops, let me get out of that view and go back to this one. If I could show the radiated field and I oscillate this thing, the idea is the changing electric field throughout space is created by the changing magnetic field throughout space, is created by the changing electric, is created by the change, etc. And so these constantly changing fields give rise to a field that is much stronger than the simple static field. This is the field that is predicted by Coulomb's law, essentially. And this is the radiated field that comes from the changing part. And we see that's hugely dominant here. So far from the source, these radiated fields are what matter. Now, we aren't going to try to understand all the math of this thing. Ooh. This gives you an idea just in the one direction. This is kind of linking this simulation to the other one. And so we can see if you oscillate this thing, we can oscillate it more frequently. Well, that just looks cool, doesn't it? And so in this case, that is what this simulation is trying to show. All right. And out of all of this, something I want you to take away from this is the fact that somebody just popped into the waiting room. Well, they're going to have to wait. Sorry, Christian. All right. Oh my gosh. All right. In this case, where was I going with this? The point of this is that we could treat light as a wave, but that there's different frequencies here. And so depending on the amount of wiggling that you get, we get different types of waves. All right. Oops, if I could get it here. So for example, visible light from about 400 up to 700 nanometers there is visible light. Below that is infrared. And you can see some applications here. We can go even lower or even higher. For example, let's go up here, X-rays, right? And notice we see that the wavelength is short for high energy. And that's something that I wanted to focus on in just a second. But all these different light waves have different wavelengths. And we can see infrared. Notice how long these wavelengths are here. Wow, let's get into radio, right? And these wavelengths are so long, you don't even see them, right? Right? Exaggerating these wavelengths would be something maybe like this, where it's going up. They're just so crazy long compared to visible wavelengths. So notice radio waves are actually on the scale of buildings and things that we live in, right? So maybe you've noticed that radio waves can be blocked when you drive under a bridge because right? So they're large enough waves, they can actually be blocked by physical structures, all right? Whereas X-rays are crazy short. All right, so out of all this, what was our goal here? right? I wanted to talk a little bit about waves are created, right? And they're going to travel throughout space in these weird patterns like this, right? And so what I'm drawing right now is the electric wave or the electric field wave, right? And so sometimes you'll see these little arrows inside of here representing the electric field is different at each point in space. All right, so at each point in space, there's a different electric field. So that's the electric field. And get this, as time progresses, at each point in time, this shape will change. So we see that the electric field in time and space, it's going to vary throughout time and space, right? And I can't see very well, so let me get rid of some of this. In addition to this, there's a magnetic field here, right? Let's see. E goes to B. Okay. So you could have a B field pointing this way, and then there'd be almost none here. So I'm going to try and draw these like this. And the idea here is you could imagine the B field is oscillating this way into and out of the page. The electric field is oscillating up and down like this. And so this is the B field wave. And they have a wavelength, which we're going to use the symbol lambda. They have a frequency, which we're going to use F. It's frequency. All right. It turns out there's going to be a couple of other parameters here. K is equal to 2 pi over the wavelength, and this is called the wave number. All right. Now, the units of a wavelength, these are meters. So the units of a wave number must be 1 over meters. The units of frequency are hertz, but we can convert those into angular frequency, which are in radians per second. All right. And we see that there is a range of frequencies that can be used, and that was called the E&M spectrum. So we see this other equation I alluded to earlier. The energy of a photon is called HF, is equivalent to HF, where H is a constant. This is frequency, and this is Planck's constant, some number. But out of all this, we see that there's this general trend, which is described on page 226 in your workbook, just before question 33.1, right? So if I could go to a different board here and finish this. We saw that there's a thing called the EM spectrum, right? And it looked, you could view it vertically, horizontally, however you want. But the idea is there's just a tiny range in here with some red light and, whoops. Maybe some green light and some blue light, right? And as we saw, right, there's infrared, and then there was radio waves and microwaves down here. Making sure I'm not screwing up the order. All right. And so these were long wavelengths, long lambda. All right. Now, or you could consider them low frequency. Now, if you have a low frequency, that corresponds to low energy, right? So low energy photons have low frequencies and long wavelengths. At this other end, we're going to get stuff like UV and X-rays, right? Or you could even get to gamma rays. All right. So in this case, these are high frequency, high energy photons. And these would be short wavelengths. All right. So that's kind of crucial. Now, which color? Well, all right. So that's pretty good. And maybe I'll end with this little puzzler. Which one of these colors of light is going to travel to us fastest from the sun? So I want you to keep in mind that, so I like to think of infrared as being low energy, which reminds me that red is the low energy end of the spectrum here. Blue would be the high energy. So which light would travel to us faster from the sun? Red light or blue light? The answer, trick question, they all travel at the speed of light. All of these waves travel at the speed of light through a vacuum. So if you're in a vacuum or in empty space, all same speed. And that speed is equal to c, which is 3 times 10 to the 8th meters per second. And if you look on the back of your workbook there, somewhere in there, I believe that's given to you. I have it somewhere. Maybe let me go to that page, sorry. And we can actually write this in terms of other constants this way. So that's what I thought you might find interesting. Oops, that's supposed to be an epsilon. Okay, making sure I don't screw it up. Got it. So it turns out the speed of light is actually equal to 1 over the square root of these two physics constants we've been using all. All right, and so we can start to, well, from here, what we're going to do is develop some equations to analyze this, but hopefully this gives you a conceptual overview of where waves come from. And maybe I have a demonstration to show you really quick as well, just to prove this is not nonsense. All right. The idea here, just to show you that you can actually transmit energy. So that's a principal attribute of a wave, right? A wave is carrying energy from one place to other. It's pretty complicated. So right now, what you can see, I have this oscilloscope here, and I'm just going to connect it to the leads of this function generator. And I'm going to auto scale it here. All right, there we go. And so right now, I see that this is a sine wave being produced by this. Now, in order to make this show up in class, I'm actually going to use a different type of antenna. I'm going to use a ring antenna. So rather than using just 2 pieces of metal, what I'm going to do is I'm going to send in alternating charges into here, like this. Right? And now what I could do is go over to this one and detect it. Right? And so what we're seeing here, to be clear, this is not connected to anything, right? What's happening is this coil is connected to AC power operating at about 1 kilohertz. It looks like it's about 983 hertz, I believe. Yes, so that's about 1 kilo, right? And then in this coil, we see that it's picking up. Now you can think about this another way, right? In this case, you could think, imagine I'm producing a magnetic flux this way, then I'm producing a magnetic flux this way, right? So I'm changing the flux through this loop. And that's another way you could think about this as happening. So in this case, now I claim I can prove to you that this coil is not connected to this coil electrically by just disconnecting this thing, right? And we see that the signal goes to Mushburger here, right? So let's put that back in. And what I'm going to do, let this auto range. I'm going to take the auto ranging off, right? And so now again, if I disconnect this circuit, right, we see that this coil is maybe picking up other radio waves from local radio stations, but it's not picking up this one anymore, right? Here's another interesting attribute, right? So in this case, you could even turn this loop and notice when we change the direction of the loop, right, we're negatively impacting the flux through this antenna here. All right, but anyways, this is a way we could actually visualize energy being transferred from one place to another It's very similar to these electromagnetic waves that we were looking at the front. Not exactly the same, but all right, that gives you an idea that this can occur. Let's call that good.